At the entrance to critical infrastructure, like the campus gate at Benha University, the daily flow of thousands of vehicles collapses into a single mechanical choke point. Security teams currently rely on manual visual checks to clear vehicles. During peak hours at the start and end of the day, this human processing time compounds, creating massive traffic bottlenecks. It also forces facilities to pay continuous, round-the-clock wages just to keep the barrier moving. But the mechanical delay is only half the problem. Manual operation leaves zero digital footprint. If a security incident occurs, there is no searchable archive of entry times, plate numbers, or vehicle images to audit. Securing a modern facility requires processing vehicles as fast as data packets. The barrier to entry has to be fully automated, removing the human bottleneck entirely. A team of engineering students at Benha University designed a solution, the LPR Gate, an AI-powered license plate recognition and smart gate automation system. The design parameters for this project were exceptionally tight. The system had to process vehicles instantaneously to eliminate traffic, and it had to be built using off-the-shelf components with a total hardware budget of roughly 3,500 Egyptian pounds. The core engineering challenge lies right here. The system must take probabilistic, unstructured data, raw pixels from a live webcam, and accurately translate it into deterministic physical actuation to move a gate. Relying on a remote cloud server introduces network latency that ruins real-time operation. The solution is a contiguous, full-stack edge AI pipeline running entirely on local hardware. An effective automated gate requires a synchronized relay race between fast vision processing, robust back-end logic, and physical mechatronics. The data journey starts at Phase 1, optical processing. A standard high-definition USB webcam captures a live video stream, feeding raw frames directly into an OpenCV software environment. The first computational hurdle is isolating the target. The system has to instantly locate the exact pixel coordinates of a small, fast-moving license plate amidst glaring headlights, shadows, and background noise. To achieve this, the engineers deployed Ultralytics YOLO V8 Nano, a specific object detection neural network. This chart plots various AI models by inference speed and accuracy. Notice the position of YOLO V8 Nano. It sits in the extreme low latency quadrant, sacrificing a slight degree of absolute precision to maximize processing speed. Because the code runs entirely on localized edge hardware, computational overhead must be kept to an absolute minimum. Millisecond latency is far more valuable to traffic flow than pixel perfection. YOLO V8 Nano's role is not to read the numbers on the plate. Its only job is to crop the target pixels out of the raw frame fast enough to keep the data pipeline moving. The isolated plate image immediately passes to Phase 2, extraction. Here, an optical character recognition engine, like EasyOCR or PaddleOCR, attempts to extract the text. Real-world optical data is messy. Dirt on the plate, harsh overhead lighting, and complex Egyptian Arabic script inevitably force the OCR engine to make occasional reading errors. If the system queries a rigid, exact match database, a single misread character will cause an authorized vehicle to be rejected, immediately backing up traffic. To prevent this, the engineers implemented a software layer safety net, the Levenshtein Distance algorithm. This algorithm calculates edit distance, the exact number of single-character edits required to mutate the OCR's flawed guess into the verified baseline stored in the database. By setting an acceptable edit threshold, the Fast API backend correctly identifies and authenticates an authorized vehicle, easily absorbing minor AI hallucinations without stalling the process. True operational reliability at the edge is not achieved by attempting to build a flawless camera. It is achieved by engineering algorithmic fault tolerance directly into the matching logic. Once authorized, Phase 3 begins, actuation. The Python server logs the vehicle, the timestamp, and the image into an SQLite database, satisfying the requirement for a fully searchable digital archive. Now, the system faces its final hurdle. The Python backend must reach out of its purely digital domain and physically alter the real world. This requires the PySerial library. It translates the digital access granted state into a raw byte command and fires it down a physical USB cable. Waiting at the other end of that cable is an Arduino Uno R3 microcontroller. The Arduino serves as the hardware translator between computer logic and electrical current. The microcontroller parses the incoming serial command and instantly routes operating voltage to the final component in the chain, an MG996R metal gear servo motor. Driven by high torque, the servo smoothly lifts the gate barrier exactly 90 degrees upward to instantly clear the lane. The successful operation of mechatronics relies entirely on this exact handoff. A string of verified software code is transformed into a physical burst of mechanical torque. Looking at the entire architectural flow from start to finish reveals the strict cohesion of the pipeline. A photon hits the camera lens and is digitized into a raw frame, where YOLO V8 instantly isolates the plate. The Arabic text is extracted and mathematically measured against the database whitelist for fuzzy similarity. The approval byte fires over the serial connection, triggering the microcontroller to blast operating voltage straight into the motor. This entire sequence, from the initial photon hitting the glass to the physical movement of heavy steel, executes autonomously in milliseconds. The LPR Gate serves as a functional model for applying localized AI to specific civil engineering challenges, demonstrating how decentralized systems can resolve immediate traffic bottlenecks. Highly effective, secure infrastructure does not inherently require massive cloud computing arrays or multi-million-dollar enterprise contracts. By intelligently layering an off-the-shelf software stack like FastAPI and OpenCV with budget microcontrollers, complex security automation can be engineered entirely locally. The team achieved high-speed throughput, total digital accountability, and extreme hardware affordability. Automation at the edge succeeds when the physical world is managed through targeted, fault-tolerant pipelines rather than infinite computing power.